Okay, so we write momentum as an integral, and then we have a body term and a flux term, right? So let's just consider this dp dt, lowercase t for linear momentum, okay? So this is equal to right? So this is a volume integral. And then we have a flux term. Let's make sure I get it right. X. That's a surface integral. So this is a volume term. Or flux term. Okay? So one assumption comes right into play. We said steady, so that turns out. Just leaves this flux term over here. Before we expand out, we'll just consider a little more things. So first you have this V dot N. Right? So the V dot N, right, when we had our velocity profile, right, we only had arrows in the x direction, right? We didn't, right, these are all parallel to the x coordinate. So this can be a vector field, right, where it would have an x component, an r component, and the theta component, right? But, right, if we said that there's no pressure difference, right, the pressure is only a function of the axis distance, that actually makes this go away and the other ones go away. So you only have an x component. So then in my control volume, what this dot product does is it's just going to recover another x component with the flux. Maybe you can say that again, but slower. In our control volume, right, the normal vectors to the surface look like this, right? And then when I get to this side, it will now look like this. And again, all of my whole vector field is parallel like this. So here's one of my vectors. So these are parallel, so their dot product is non-zero. These are perpendicular, so their dot products are zero, identically zero. So that's just something we can reason with this term right here when it comes to this control volume. Same with this thing. Here, the normal vector to the surface is pointing this way, so when I dot it, I'll get a negative orientation. But regardless, top and bottom, this vector field dotted with these ends is always going to be zero, so you'll just recover the x part of this velocity we're trying to quantify. Okay? So then what do we get? Well, back it up. So I have to integrate This is what I have to integrate over the entire surface, where my surface is a cylinder. Well, this just becomes a U, right? A U. So this is right. This is U. This is U. So that term becomes a U squared. I get two of them. Second part is this dA term. So what's a little differential area for a cylinder control volume? Well, from calculus, you can do, using Calc 2 exercise, you can show that a little bit of area, right, that a little bit of area turns out to be, right, a 2 pi r dr. Remember this r dr. So this is important for this whole formalism that they have. We picked up an extra r and we're looking for U of R, right? Yeah, extra credit is show this. Show that why a little bit of area for a cylinder is this. Should have done it sophomore year. All right. Still not done. Now you just integrate over the entire area. So how we're going to do that? Can you see that? Oh, light. So now we have to go from the positive R down to the negative R based on the thing we have. You can flip this. Okay, and I've written the same thing twice. These are identical, so we get 0. All right, so that was just this side of our force balance for the control volume. Up next, we'll look at just the sum of the forces. This one's easier to understand, I think.